Alright, so in this session we are planning to discuss more MCQs from pH, and this is the first question we have covered from 2017 to 2021 in one of the previous sessions. So let's start from 2016 and work our way backwards. A buffer solution can be prepared by weak acid, Ka is provided, weak acid, and a strong base. Yes, the ratio of the concentrations of acid to base needed to prepare a buffer solution at pH equal to 6 is. The ratio of concentrations of acid to base needed to prepare a buffer solution at pH equal to 6. So when they say pH is equal to 6, when pH is equal to 6, right, pH is equal to 6 means H3O plus concentration is 10 to the power minus 6 mole per decimeter cube. Right, so the question is, what is the acid to base ratio of concentrations of acid to base? Now when an acid and a base, they're talking about the acid and the strong base probably. Now when an acid and a base react with each other, for example now HA reacting with sodium hydroxide, you will be getting NaA plus water, right? Okay, now we can't consider that they are equal volumes of them are mixed. Can we say that? Or else if we go to the Henderson's equation, we know Henderson's equation goes like this. Now we will pH is equal to pKa minus log 10 concentration of acid over concentration of salt. This is how it goes. They are talking about acid to base concentration, acid to base. Now if Ka is 4 into 10 to the power minus 7, we can find out pKa. How do you do that? pKa is equal to minus log 10 Ka. So that is minus log 10 4 into 10 to the power minus 7, that is equal to 7 minus log 10 4. Log of 4 is roughly 0.602, so it is 7 minus 0.6, that is roughly 6.4. Okay, so here if I put pH equal to 6, this one equal to 6.4 minus this value log 10 concentration of acid over salt. So if this comes to the other side, log 10 concentration of acid over concentration of salt, that is given by 0.4. So this salt is this, and acid is the remaining acid in the after the reaction finishes. Then concentration of acid over concentration of salt is in fact 10 to the power 0.4. This is antilog of 0.4. Antilog of 0.4. So what is the antilog of 0.4? It is 2.5, something like that. So which is roughly equal to 5/2. So is that the answer they have given for this question? This is what we find here is acid or over salt ratio. So by base, do they mean the strong base or the conjugate base? That's the confusion I have in this question. Because to find the concentrations of these, the number of moles can be compared. If we have to assume that they are mixed in equal, what do you call that? They are mixed in equal volumes, and then that's the issue. So if you do it this way, people, we are getting 5/2. Can someone check the scheme and tell me if they have got 5/2 or some other answers? Just directly have applied Henderson's equation. Not if they're talking about the strong base concentration and everything, we will have to take the concentration of this as C1, concentration of this is C2, and the volumes, even if you take, see, buffer solution can be prepared by mixing a weak acid and a strong base. That's all they have mentioned. So I think we have to go this way. There's no other way we can approach this question, right? Okay, so let's go ahead, because they have not given the volume, people. Without knowing the volumes, we can't find out the number of moles and remaining number of moles and all those things. They have not said they are mixing equal volumes, so probably they are going in this direction. Right, answer is fifth one. And yep, then we'll move on to the other questions. 2015. The pH value of a solution which contains a weak acid and its sodium salt is A, right? Oh wait, sorry, this one. 2016 we missed. The solubility of barium oxalate, the conjugate acid, barium oxalate is less in acidic aqueous medium than in water. That is wrong. That is wrong, because barium oxalate can dissolve very well in acidic medium. Barium oxalate can dissolve very well in acidic medium. The conjugate acid of C2, the conjugate acid of C2O4 2 minus is the weak acid H2C2O4. Is that correct, people? That is also wrong, because this is wrong. Conjugate acid of this means they are taking this as the base now. So C2O4 2 minus will react with water and it will produce HC2O4 minus and hydroxide. No? Yes. So if I take this as the base, this is going to be the conjugate acid. The solubility of barium oxalate, okay, this one I'm going to explain next. This is based on equilibrium and solubility product. Why is this incorrect? We know barium oxalate solid, it dissociates to barium 2 plus aqueous and oxalate aqueous, right? Now, usually it doesn't dissolve well in water, but when you add acid, so what we are adding is, I'll put it this way, I'll put an arrow like this so that you can understand. When acid is added, or to make it acidic medium, you have to add acid. When acid is added, if you're adding acid, who are you adding? Actually, you're adding H plus. So when acid is added, C2O4 2 minus will react with that H plus and it will combine with that H plus for some extent. You will be getting HC H2O4 minus, and yeah, that's it. This, you'll get this product. So what is happening? Since this can happen only because this is a conjugate base of weak acid. Since C2O4 2 minus is a conjugate base of weak acid H2C2O4, C2O4 2 minus has the ability of reacting with H plus, or of combining with H plus, reacting and combining with H plus, combining with H plus. So what will happen? What will happen if hence when C2O4 2 minus ions are removed due to the addition of H plus, equilibrium will shift forwards. Equilibrium, we are removing the product. When you remove the product, we know equilibrium will shift forwards. Equilibrium will shift forwards. If equilibrium shift forwards, this will dissolve. So barium oxalate dissolves more. This is what happens. So this is exactly what happens in barium compounds like barium carbonate, barium sulfite. If you take barium carbonate, barium carbonate can create an equilibrium. This is a sparingly soluble compound. It doesn't dissolve in water. Carbonate is there. So does it dissolve in acids? Yes, we should know that from inorganic. When I add H plus, what happens? When I add H plus, it can combine, carbonate can combine with H plus and turn into HCO3 minus. Therefore, reaction can move forward. So this will dissolve more in acidic medium. We have studied that. Why does it happen? Why does this happen? Because H2CO3 is a weak acid. That's why it happens. And another example which we regularly use in inorganic is this. What is that? Barium sulfite, BaSO3 solid. That also will create an equilibrium like this in its saturated solution. And for that, if you add acid, what's going to happen? Same scenario is going to take place. When I add acid, what's going to happen? That H plus is going to combine with SO3 2 minus and form HSO3 minus. Reason again, because H2SO3 is a weak acid. It's a weak acid. The black paragraph, since H, sorry, yes, HCO3, sorry, okay. This, but now these two are okay. These two dissolve well in acid. Oxalate also like that. But tell me someone who doesn't dissolve in acid. A barium salt which doesn't dissolve in acid. We have learnt in inorganic many times. Barium sulfate, exactly, barium sulfate. Now we need to know why it doesn't dissolve in acid. We have learned it many times that barium sulfate is a white precipitate which does not dissolve in acid. The reason is this: barium sulfate will create an equilibrium where barium 2 plus and sulfate are produced. Sulfate is a conjugate base of a strong acid. So when you add H plus, we will not be getting HSO4 minus. That won't happen. Why won't it happen? Because H2SO4 is a strong acid. Strong acids don't attract H plus. They don't combine with H plus, no? They always release H plus. I hope you guys understood the difference. So barium carbonate, barium sulfite, barium oxalate, they can dissolve in acidic medium, but not barium sulfate. Same goes with silver chloride. If you take silver chloride, chloride will be released. Chloride can't combine with H plus. Silver bromide, silver iodide, all of them are like that, because Br minus, H plus Br minus is HBr. HBr is a strong acid. Hi is also a strong acid, but silver fluoride, AgF, can dissolve in water because F minus is conjugate base of HF, which is a weak acid. So likewise, right, done. Then we'll move on to the next question, that is 2015. 2015, the pH value of a solution which contains a weak acid HA and its sodium salt NaA is simple A. Inam, need a help. Did you check the answer for the previous question we did? That buffer solution 2016? What was that? The answer they had given? Hold on. All right, sorry, okay. Sorry, let's continue. If the value of the concentrations of HA and NaA ratio is increased by 10 times, the new pH of the solution will be right. Okay, so Inam says for the previous question, I think I also had a small issue with that. Sparse paper says all. Can you remember, people, we had a problem with this question? It says acid to base ratio, but all we can find is acid to salt ratio. We can't find out acid to strong base ratio unless they have given the volumes of the acid and strong base, because we don't know what number of moles of each reacted. So I think they should have rephrased this as acid to conjugate base ratio, if not acid to salt ratio. And if you directly use Henderson's equation only, we are getting 5 by 2, which I explained earlier at the beginning. Other than that, we can't do anything about this question. Maybe that's why they have given all as the answer. Right, so since that is sorted out, let's move on to the other question. Here. Right, 86, that is 2015. Take 2015. Yeah, circling around it over and over again. If the concentrations of HA to Na ratio is increased 10 times, right, again Henderson's equation should be directly applied, no people, because pH is equal to pKa minus log of concentration of acid over concentration of salt. In other words, it is in fact pKa minus log of concentration of HA over concentration of NaA, right? So there are two scenarios. For during the first scenario, they have given pH is how much? pH is A, simple A. pKa, there is no change as long as temperature is not changed, minus log of this ratio, will take it as HA into HO over Na, right, initial concentration. If not, I'll take that as log of X, where X is equal to initial HA over NaA concentration. I hope that's understandable. HA to Na ratio. Concentration of HA to Na ratio, they will take it as X, right? And in the second situation, now we need to find the new pH. So that is pH2 equal pKa doesn't change as long as you don't change the temperature, minus log of, instead of HA concentration over Na concentration, I have to put 10x. Why should I put 10x? Because they are saying if the value of concentration of HA to Na ratio is increased 10 times, that's why this, right? X is equal to initial HA concentration over Na concentration. Now it is 10x. Then what is the plan? We need to get rid of X and pKa. There's only one way to get rid of them, that is subtracting. So you subtract the first one from the second one. Here we will be getting pH2, which the new pH we are supposed to find out, minus A equal to pKa. pKa will get cancelled out, and I'm getting log X minus, if it is confusing, I'll do it this way, minus log 10x minus log X. So pH2, which we are supposed to find out, equals to, here I can say log X, this minus and minus becomes plus, no, log X minus log 10x, and this minus A comes to the other side, becomes plus A. And how about this one? There are two log values which are subtracted, so you can write them inside the log and you can divide them, x over 10x plus A. Okay, so x inside the log will get cancelled out like this. I hope you guys understood what log A minus log B can be written as log of A over B, O level. And then finally I have log 1 over 10. Log 1 over 10 is what, people? Log 1 over 10. Log 1 over 10 can be written this way. pH2 is equal to log 10 to the power minus 1 plus A. What is log 10 to the power 1, 10 to the power minus 1 plus A? That is minus 1, minus 1 plus A. Whatever the power you have, whatever the power of 10 you have inside, it comes out. So new pH is going to be equal to A minus 1. A minus 1. That's all. Just a matter of writing Henderson's equation, substituting the values and getting the answer. Simple as that. So please remember the equation if you want to do MCQs quickly. Otherwise, you will be in trouble. This equation you have to remember. Done. And moving on. Next, that is 2015. Then we'll go to other questions. That is 2014. Yep. Oxalic acid is a diabasic acid with K1 equal to 5.4 into 10 to the power minus 2 and K2 equal to 5.3 into 10 to the power minus 2. What is the equilibrium constant for the reaction given below? Right, that is also quite simple. We have done when they give Ka of 2 steps, then finding the Ka of both steps combined together. We have done these questions several times before. Let's take a minute and finish this off. Now for oxalic acid, the first dissociation will happen like this. It will react with water and it will release one H3O plus ion first. When it releases one H3O plus ion, this will become HC2O4 minus, and here H3O plus. And the next one, HC2O4 minus aqueous, will be reacting with water and will turn to C2O4 2 minus plus H3O plus. So this is going to be K1, this is going to be K2. Now what we have to understand is, in that resulting solution, final solution guys, we will be having 4 different species. H2C2O4 will be there. Okay. HC2O4 minus will be there. C2O4 2 minus will be there, and H3O plus will be there. All 4 of them will be mixed up together like this. So this H3O plus concentration is common for both the equilibria. Hope you guys understood that. Okay, it's common for both the equilibria. Therefore, As usual, we know if we write K1 is equal to concentration of HC2O4 minus into concentration of H3O plus over concentration of H2C2O4, and that is equal to 5.4 into 10 to the power minus 2. That's the first equation. And if you write K2, that is equal to concentration of product C2O4 2 minus into H3O plus over HC2O4 minus, and that is equal to 5.3 into 10 to the power minus 4. Second one. Now this one, they are asking for equilibrium constant of this equilibrium. We'll take this as K. Now what is K, people? K is equal to concentration of H3O plus squared concentration of C2O4 2 minus divided by concentration of HC2O4. So if you want to get K, what should I do? H3O plus squared means there's only one way, multiplying 1 and 2. Yeah, multiplying 1 and 2. You multiply 1 and 2, 1 into 2, that will be K1 K2. K1 K2, that is going to be equal to, when you multiply those two, what? HC2O4 minus and this HC2O4 minus will get cancelled out, and we will get that equation which we need. C2O4 2 minus and H2C2O4, which is equal to our K. Yeah, so K is equal to K1 into K2. K1 is 5.4 into 10 to the power minus 2. K2 is 5.3 into 10 to the power minus 4. When you multiply 5 into 5, it will be roughly around this. I think third will be an appropriate answer. 5.4 into 5.3, I think it's 29 into 10 to the power minus 6, which is equal to 2.5 into 10 to the power minus 5 mole squared decimeter minus 6. I didn't bother multiplying them because 5 into 5 25, so it should be a 20 odd or 30 number. There's only one number which is close to that, and that should be the third answer. Simple as that. This is a very simple question. You shouldn't have any issues with this. This is even, yeah, very easy, very easy. There's nothing about pH here. It's about writing the two steps and multiplying them. Next, okay, solubility product of sparingly. So now, yeah, we have solubility product and pH both involved here, which we have covered recently. Solubility product is also done. Let's quickly to finish this. The solubility product of the sparingly soluble hydroxide MOH is 1 into 10 to the minus 8. The pH of a saturated solution of MOH is I don't know, I mean, it's just sparingly soluble. That means this is going to be definitely M plus and OH minus, correct? So they have given us the solubility product. So if there's only MOH, there's no common ion effect or anything. If X moles of MOH dissolves in 1 decimeter cube of water, X moles of M plus ions will be released in 1 decimeter cube of water. X moles of OH minus ions will be released in 1 decimeter cube of water. And for this we write KSP. How do you write KSP? We write KSP is equal to concentration of M plus into concentration of OH minus. Now concentration, sorry, KSP is provided there, 1 into 10 to the power minus 8 equal to x, if not, yeah, x into x, never mind, x into x, which is x squared. So x is equal to 1 into 10 to the power minus 4. X is OH minus concentration, which is equal to 1 into 10 to the power 5 minus 4 mole per decimeter cube. And if OH minus concentration is 1 into 10 to the power minus 4 mole per decimeter cube, now answer 4 is there. Careful, this is not H plus concentration. They're asking for pH. So I need H3O plus concentration, but what I have is OH minus concentration. If OH minus concentration is that, I can say POH is equal to 4, isn't it? POH is equal to 4. What is pH? we all know pH is equal to pKw minus POH, and under normal 25 degrees Celsius condition, pKw is 14 minus 4, answer is 10. Simple as that. Answer must be 10 for question from 2014, and that is the fourth answer. Okay. Done. Very straightforward question. Next we have another pH related question, I believe. Right, let's start. A volume of 50 centimeter cube of 0.01 mole per decimeter cube sodium hydroxide solution was added to 50 centimeter cube of 0.11 mole per decimeter cube solution of the weak acid HA. Same volume this time. See, in this question they have given the volume, unlike the 2016 question, the buffer solution question we had an issue with. The pH of final mixture was found to be 6.2. If K2 is the dissociation constant of the acid, which of the following answers indicate its pKa value? Right, so we have to find Ka value of the acid. For that, people, this is what we have to do. Sodium hydroxide, okay, what is the initial number of moles of sodium hydroxide? Initial number of moles of sodium hydroxide, that is concentration into volume. What is the concentration? 0.01 into volume is 50 to 10 to the power minus 3. That is 0.5 into 10 to the power minus 3 moles. Okay. Similarly, initial number of moles of HA, that is concentration into volume. What is the concentration? 0.11 into 50 into 10 to the power minus 3. So that is going to be 5.5 into 10 to the power minus 3 moles. So you can see we are using HA in excess, so that after the reaction finishes, HA will remain and NaA will remain. That's how we can create a buffer solution. Right, so let's go to that reaction. HA will react with sodium hydroxide to produce NaA and water. Initially, we have initial, I'll say moles, right? Then we can just put the numbers now. HA is 5.5 into 10 to the power minus 3. NaOH is 0.5 into 10 to the power minus 3. And none of these are there. And then we have to figure out the reacted number of moles. Reacted number of moles. How many? Sodium hydroxide is going to be the limiting reagent because 1:1. We have this in excess, minus 0.5 into 10 to the power minus 3 moles of that will react. Same amount of this will react, and more importantly, same amount of this will be produced. 0.5 into 10 to the power minus 3 of this will be produced. So at the end, the concentrations are important. After the reaction is over, at the end, we will have 5 into 10 to the power minus 3 moles of HA, no moles of NaOH, 0.5 into 10 to the power minus 3 moles of NaA, and we will have a total volume of 100 milliliter by then in the solution. 100 milliliter, which is 0.1 decimeter cube. That is not needed because that volume is common for both, so we are safe. What's the question now? Oh yeah, that's it, people. Then this is the final concentration of final HA concentration. That is going to be equal to 5 into 10 to the power minus 3 moles over 0.1 decimeter cube. In essay questions and all, if they ask, this is how you would do it. That is 5 into 10 to the power minus 2 mole per decimeter cube. And final NaA concentration, that is going to be 0.5 into 10 to the power minus 3 divided by 0.1 decimeter cube. That is going to be 5 into 10 to the power minus 3 mole per decimeter cube. So luckily the volumes were equal, so things did not get too a little complicated. If they had put 40 milliliter of this and 60 milliliter of this, you should be very careful. Fine then. then we have to go back to Henderson's equations as usual. Henderson's equation once again, pH is equal to pKa, which we are supposed to find out, minus log concentration of acid over concentration of salt. Who is acid? Acid is the remaining amount of HA. By salt, they mean the remaining amount of NaA. pH is 6.2. Final pH is 6.2. See, 6.2. pKa we do not know, minus log of concentration of acid. How much is that? 5 into 10 to the power minus 2. Over concentration of salt is 5 into 10 to the power minus 3. Okay, so pKa, that is going to be equal to 6.2, will remain as it is. This part will go to the other side and it will change into what? Plus log of 10, isn't it? 10, because people, yeah, log of 10. 5 and 5 will get divided. 10 to the power minus 2 divided by 10 to the power minus 3 is 10. What is log of 10? It's 1. Log of 10 is 1. Answer is 7.2. 7.2. That is the answer for question from 2013. Can someone check that, double check it and confirm, please, if you don't mind? Anyone? You know? No? Yeah, okay, thank you. Right, so that is how you do this question. A cool one. When they have given you the volumes in the initial concentrations, you have to find the remaining concentrations and then only do the question. Remaining concentration only do the question. Huh? Don't start with the initial ones, because once you mix them, they will react and then you will get a resulting solution. You have to apply the equation for the resulting solution. So if you use these concentrations directly, you are in big trouble. Next question comes from 2013 once again, but this time it's not a quantitative one, it's just a qualitative one. Which of the following arrangement shows the correct increasing order of pH of the following 1m aqueous solution? So all of them have equal concentration. Yes, that's important, because when you compare the pH for different species like this, you need to make sure that their concentrations are more or less same. Otherwise, sometimes a strong acid with very low concentration might have a lower, greater pH than a weak acid with very high concentration. So we have to make sure you compare similar concentrations. People, now how do we decide this? We know HCl. HCl is a strong acid. HCl is a strong acid. KOH is the strong base. Strong base. KOH is a strong base. So it's like, from inorganic all we have learned, it's a strong base. And this one, this is a weak acid. And this one, how do we decide its acidity or basicity? Now, when you take calcium chloride, it's a salt. When you have sodium acetate, it is also a salt. Now, when you want to decide the acidity or basicity of salt, think of their origins. Now, calcium chloride means you have to think of the base and acid which created that. Calcium hydroxide and HCl will react to form calcium chloride. Calcium hydroxide is a strong base. It's a strong base, whereas HCl is a strong acid. So when a strong base and strong acid react, this is going to be more or less neutral. That is how you decide. Both are strong and strong will neutralize each other. This. And here if you take, we know acetic acid and sodium hydroxide. They are going to form this salt. And acetic acid, we all know it's a weak acid, whereas sodium hydroxide is a strong base. Strong base, weak acid, base's dominance is more, therefore the result will be a weak base. Weak base. Okay, so we have a neutral salt and weak base. Now we can go with a common statement like this, that is for equal concentrations, for equal concentrations, that means we are using they are saying 1m pH. Obviously we can do a comparison. If pH is going to be, strong acid is going to have the smallest pH, strong acid, and then weak acid, and then neutral, and then we have the weak base, and then finally strong base. Okay, so if you're wondering what these letters are, A stands for acid, B stands for base, W stands for weak, and S stands for strong. This is how it's going to go, right? Then we have to find this order and arrange them. Fifth looks fine to me. Fifth, right, people? Fifth, look at the fifth answer. Fifth one. Okay, because normally we say for neutral it's around, it's exactly 7 for neutral. And for this strong acid, for HCl, what is going to be the pH, people? If the concentration is 1m, the H3O plus concentration is 1, it's 0. pH of HCl is 0. pH of HCl is 0 here. It's a very strong acid. HCl is 0. Acetic acid will be like 3 or 4, something like that. Likewise, neutral is 7. Here it will be, now KOH, what's going to be the pH? It's 14. Now for KOH, if, for this context, now I will underline this in what color? Right, blue color. For this concentration 1m, pH of KOH is 14. pH of HCl is 1. Not 1, 0. Calcium chloride, we can roughly say it's, I think it should be 7. Okay, yeah, more or less 7, because strong base and strong acid. And this one will be in between. This one will be in between. With 3.5, 10, something like that. We can surely say their pH without knowing their Ka values, you know. Right, but more or less we know how to make the arrangement. Done. And then we'll move on to next year, 2012. 2012, once again we have a calculation. Okay, let's focus on that. A sample of sodium hydroxide is contaminated with an inert impurity. Inert means an impurity which does not take part in reactions. 4 gram of sodium hydroxide sample was dissolved in 1 decimeter cube of water, and 50 centimeter cube of 50 cube sample of the resulting solution was allowed to react with 50 centimeter cube of 0.1 mole per decimeter cube HCl. The pH of the reaction mixture was found to be 2, the percentage purity of sodium hydroxide sample. So it's a classic chemical calculation type question, but the only part is this small part is there. The pH of the reaction mixture was found to be 2. So let's go with the process without missing anything. You have a sample of sodium hydroxide with an impurity. Sodium hydroxide is there, some kind of impurities there. So it is not fully sodium hydroxide and some other inert impurity, a non-reactive impurity is mixed there, 4 grams. And first they are adding water, and they are forming a solution of 1 decimeter cube. So inside this now sodium hydroxide is there, but you can't find the number of moles of sodium hydroxide by dividing 4 gram by its molar mass. Completely wrong. Reason is, this 4 gram doesn't consist entirely of sodium hydroxide. So what you have to do is, we have to take the number of moles of sodium hydroxide here as x moles. Then here also we will have the same x moles of sodium hydroxide, because it is completely dissolved in water. 50 centimeter cube of the sample of the resulting solution was allowed, right? So then you have to separate 50 centimeter cube of this sample. 50 centimeter cube. Of course, sodium hydroxide will be there, but the number of moles will not be X anymore. Why, people? We have taken 20 times the volume we have taken is 20 times less than the volume of the large solution. So it has to be X over 20 moles. X over 20 moles, remember. It can't be X anymore because from 1 decimeter cube is 1000 centimeter cube. So from 1000 centimeter cube we have taken only 50, and that is made to allowed to react with 50 centimeter cube of 0.1 mHCl 50 centimeter cube. So now we have to be very careful. That gives us a resulting solution of how many milliliters? Obviously 100 milliliters, 100 centimeter cube, and the pH of the remaining resulting solution is given as 2. If pH is 2, the conclusion is, so resulting solution is what? So resulting solution is acidic. Acidic. Why? Because pH is less than 7. Hence we can say, hence some amount of HCl is remaining, some amount of HCl is remaining. HCl is remaining in the final solution. Obviously, if HCl is not remaining, pH can't be less than 7, people. If pH was greater than 7, all HCl has reacted and sodium hydroxide is remaining, but it's not the case. So here, very important, the final volume is 100 centimeter cube, and pH is 2. If pH is 2, pH is equal to 2, we can say H3O plus concentration. H3O plus concentration is equal to 1 into 10 to the power minus 2 mole per decimeter cube, and that H3O plus is created on the H2O plus concentration is created only by remaining HCl. HCl is a strong acid, so the remaining HCl concentration will be equal to H3O plus concentration because HCl completely dissociates into water. So with this information I can say, so concentration of remaining HCl is equal to same 1 into 10 to the power minus 2 mole per decimeter cube. Why, people? Why is that? Because we know when HCl reacts with water, it completely turns to H3O plus and Cl minus. So whatever the concentration we have for this, if it is 10 to the power minus 2 m, that means HCl also should be 10 to the power minus 2 m. If I know the concentration of remaining concentration of HCl, using that I can find out the remaining number of moles of HCl. So remaining number of moles of HCl. How can I do that? Concentration into volume. So concentration of remaining HCl is what we have found out, 1 into 10 to the power minus 2. Volume is 100 centimeter cube. 100 here, 100 centimeter cube. So that is 100 into 10 to the power minus 3. Final answer. 10 to the power minus 2 and 100 will get multiplied and become 1 into 10 to the power minus 3 moles. 1 into 10 to the power minus 3 moles. That is the remaining number of moles of HCl, people. Right? So using this information, we can find out initial number of moles of HCl. Chemical calculation. Initial number of moles of HCl, that is concentration into volume. Concentration is 0.1, volume is 50 into 10 to the power minus 3 decimeter cube. Therefore, the final answer is 5 into 10 to the power minus 3 moles. I know the initial number of moles of HCl. I know the remaining number of moles of HCl. Using those two pieces of information, what can I find now? So reacted number of moles of HCl could be found. Reacted number of moles of HCl will be equal to, initially we had 5 into 10 to the power minus 3, at the end we have only 1 into 10 to the power minus 3, therefore 4 into 10 to the power minus 3 moles of HCl has reacted. Alright, so see the connection is made one by one. And okay, we are almost there. If that's the reacted number of moles of HCl, people, we know sodium hydroxide and HCl will react with each other, and we will be getting sodium chloride and water. If the reacted number of moles of HCl is reacting with who? Sodium hydroxide, people. If that is 4 into 10 to the power minus 3, that means number of moles of this is also 4 into 10 to the power minus 3. Okay, so I can say, so reacted number of moles of sodium hydroxide, that is also 4 into 10 to the power minus 3 moles. And what is the number of moles of reacted sodium hydroxide? That is x by 20, x over 20, because x over 20 moles of sodium hydroxide was there in the 50 milliliter solution when we added HCl. That is equal to 4 into 10 to the power minus 3. Therefore, x is equal to 80 into 10 to the power minus 3 moles. X is the initial number of moles of sodium hydroxide in the 4 gram sample. Then we can quickly finish this off, people. How do we do that? We can find out, first let me find out molar mass of sodium hydroxide. That is 23 plus 16 plus 1, and it is 40 gram per mole. So mass of sodium hydroxide in the initial mixture will be the number of moles into molar mass. We just have found the number of moles, 80 into 10 to the power minus 3 into molar mass is 40. I think that will be 3.2 grams, because it's 3200 into 10 to the power minus 3. That is 3.2 grams. The question is percentage purity of sodium hydroxide. So we have found the mass of sodium hydroxide in that total 4 gram sample. So if I say percentage purity of sodium hydroxide, that is going to be mass of sodium, percentage purity of sodium hydroxide. That is going to be mass of sodium hydroxide divided by total mass, or mass of mixture rather, multiplied by 100. 3.2 over 4 into 100, and that is obviously what, 80 percentage, because 3.2 over 4 is 4 over 5. 4 over 5 into 100 is 80 percentage. The answer is 4th one. Okay, so this question is more or less chemical calculation. Only part we have to be mindful about is that 2, pH is 2. pH 2 means that it says H2O plus concentration in the remaining solution is 1 into 10 to the minus 2. Even when you were in grade 12, if they had given the concentration of H3O plus in the remaining solution, you should have been able to do this question. Alright, you don't need any special pH knowledge to do this question. The only bridge between this question is pH is the fact that you should know how to convert pH to H3O plus concentration. That's it. Okay, right, a good question, but a lot to be mindful about. This connection must be made correctly. If not, you will get an answer which is greater than 100 percentage. That's important. And other than that, this part is going to be crucial. How to find the remaining concentration, remaining number of moles of HCl, then reacted number of moles of HCl, and that should be equal to sodium hydroxide. Likewise, we have done questions like this in past. So yeah, and with that, we'll move on to the next part. 2012 done, and then 2011. Right, what is this? 2011. The pH of a dibasic acid in which the first ionization constant is K1 is higher than the pH of monobasic acid of the same concentration and same ionization constant K1. A lot of information provided. It's better if you can put it into an equational form, no? Right, what is the strategy? This is how it's going to be. They are talking of comparing two acids. Or the two acids, people. We have H2B, or H2A, let's say H2A, and the other acid is H2A is diabasic acid, diabasic weak acid. Whenever they say ionization constant, it definitely has to be weak acid people. And then we'll say HB. B is that ion, that is monobasic weak acid. Monobasic weak acid, right? Now, if you take diabasic weak acid, it's going to do this, no people. It's going to do this. I mean, it will dissociate in 2 steps. H2A will react with water, and it will dissociate first. It will create HA minus while releasing H3O plus. So for this, they have given the dissociation constant as K1. All right. It doesn't stop there. This will also dissociate a little bit, not as much as the first one, of course, but it will still dissociate. It will still dissociate, and you will be getting, sorry, you will be getting again, finally we will have A2 minus and more H3O plus. So what I'm trying to, we'll take this as K2. We don't know what K2 is. What I'm trying to say is H3O plus is not released only during the first dissociation. Some more H3O plus will be released by the second step as well. So these are the 2 steps for the diabasic weak acid. On the other hand, if you take this acid, it's just 1 step. HB will react with H2O liquid, and it turns to B minus and H3O plus, of course. So here you get H3O plus released only by 1 step, right? So K1 is same, K1 is same. The K, I mean the dissociation constant is same. Let's assume that these two were equal concentrations of they were used. Otherwise, we can't make that comparison. So they are saying the pH of dibasic acid in which the first ionization constant K1 is higher than that. No, I don't agree with that. Now here we will be getting H3O plus concentration. I'll take the H3O plus concentration to be X1. Okay, and here H3O plus concentration, let's take it as X2. Which one is bigger, X1 or X2? X1 or X2? Which one is going to be bigger? Obviously, X1 is bigger than X2. X1 is bigger than X2 because more H3O plus will be released by the first acid. More H3O plus will be released by the first acid. If X1 is bigger than X2, what is the conclusion? In other words, yeah, but you know, but when H3O plus concentration increases, okay, pH decreases. So what about pH? pH of H2A will be less than HB. More H3O plus concentration means less pH, but this statement says otherwise. Read it carefully. The pH of diabasic acid in which the first ionization constant is K1 is higher. This part is the wrong, incorrect part. Should be lower. I have explained everything step by step. The acid strength of a substance depends only on the number of ionizable hydrogen atom present in its molecule. What about that? The acid strength of a substance depends only on the number of ionizable hydrogen atoms. That is wrong, no people, that is wrong. That's completely wrong. You know what this statement says? This statement means if there are more ionizable hydrogen atoms, it will be a stronger acid. That's completely wrong. For example, now H3PO4 has 3 ionizable hydrogen atoms, but still it is a what? But still it is a weak acid. right? Hi has only one ionizable hydrogen atom, but it is a very strong acid. It's even stronger than HCl. So you can't decide the strength of an acid based on the number of ionizable hydrogen ions. That's completely wrong. Therefore, I think we should settle to which answer? Both are wrong means fifth answer. Done. Moving on. Okay. I think should be small, right? Yeah, we'll finish this. 2011. So I think we have covered last 10 years, which is good. We had only covered last 5 years before this. 10 years now. Which of the following statements are true regarding the equilibrium given below? Yeah, this is the equilibrium. That is the dissociation of water. H3O plus concentration into OH minus concentration is greater than 1 × 10⁻⁴ moles cube decimeter minus 6 at temperatures above 25 degrees Celsius. I think that's correct. We have discussed that point earlier. Now this reaction is what? This reaction is endothermic. Endothermic because bonds are broken. Bonds are broken, so definitely energy is absorbed. So to explain A, when temperature increases, what will happen? When temperature increases, equilibrium shifts to endothermic side. That is this way. So we can say H3O plus concentration and OH minus concentration increase. At 25 degrees Celsius, we know H3O plus concentration into OH minus concentration is equal to our Kw, which is 1 × 10⁻⁴ mole squared decimeter minus 6. So at temperatures greater than 25 degrees Celsius, obviously the multiplication, it's going to be more than the value at 25 degrees Celsius. Right, first one is correct. If first one is correct, there are only 3 options we have left. 1 or 4 or 5 are the possibilities. 2 and 3 can definitely be wrong. It exists in any aqueous weak acid solution. Yes, correct. It exists in any solution. Any solution. Not only weak acid, it can be weak base, strong acid, any solution, this will be there. Okay. It exists in any solution. Exists in any solution. Doesn't have to be specifically weak acid or weak base. It is an exothermic reaction. Wrong. It should be endothermic. Why do I say it's endothermic? There's a logic behind that. No, we can't by heart it. Why? Because bonds are broken. H2O is a molecule. From H2O, if you are releasing ions, you have to break the bonds. H3O plus aqueous is equal to OH minus OH minus concentration for any aqueous system. That is wrong. Why, people? Because for acids, H3O plus concentration is usually larger than OH minus concentration. There will be, even in acids, there will be a little amount of OH minus concentration, remember, and for bases it should be the other way around. H2O plus concentration will be less than OH minus concentration. And only for neutral solutions, those two will be equal. So first and second are correct answers too. So it's pH questions are not always about number crunching, it's also about qualitative understanding like this as well. Done. Okay, right, then moving on to the next question, that is 2011. 2011. the percentage ionization of aqueous solution of 0.1 m HCOOH formic acid at 25 degrees Celsius is, oh, easy, directly percentage ionization. Wow, percentage ionization means people degree of dissociation, that into 100 alpha. The alpha we put is fractional fraction of ionization, but they are asking for percentage, so we have to find alpha, then you have to multiply it by 100, then only you will be getting percentage ionization, remember. Okay, right, because I see 0.44 and 40, highly likely that one of these three is going to be the answer, but let's see, let's hope for the best. We all know when there's a weak acid, if you want to save time, you can certainly go with this, people. What is that equation we use? Ka equal to C alpha squared. If you can remember this equation, you can save a lot of time. Yeah, you can directly use that equation. That's what I was saying, because it's an MCQ. They will not look for your steps. If not, yeah, now ask me, can we use this equation? Now when you make alpha the subject, it's going to be square root of Ka over C. So Ka is directly provided. What is Ka? 1.7 into 10 to the power minus 4 divided by concentration of C, this 0.1. Right, if you multiply up and down by 10, you will be getting 17 into 10 to the power minus 4, right, and then square root of 17 into 10 to the power minus 2, that is our alpha, wait, is equal to this, alpha is equal to square root of 17 into 10 to the power minus 4, alpha is equal to square root of 17 into 10 to the power minus 2. People, this one what we have found here is not percentage ionization, this is fractional ionization. So percentage ionization will be, so percentage ionization is equal to 100 alpha, that is 100 into root of 17 into 10 to the power minus 2. Final answer is root of 17. Now root of 17, they have almost taken, it's approximately it's equal to what, 4, because it's approximately equal to root of 16 kilogram, they have taken it as 4. I don't see any answer saying 4.1, 4.2 anything, so there's only one answer which is close to 4. Okay, in essay questions, no, don't do it. In essay questions you have to write the equilibrium, only get it. Okay, so I highly recommend you to remember this equation, which will help you save a lot of time, people. This one or this one for that matter. If they have given only a weak acid, you can use this equation. If they have given a weak acid with a base or something, the weak acid, you can't use this directly, because the concentration of H3O plus and concentration of H3O plus and A minus will not be same there, people. But if they have given just a weak acid, you can use this equation, which will save you a lot of time. If not, if you cannot remember that for some reason, that doesn't mean you can't do the question. Of course you can do the question, but you will have to go through a bit of a trouble. Let me just show that quickly. What do we do? I'll quickly say this HCOOH reacting with water. Let's say sometimes you might not, this might not click, might forget that. When you get a little tensed and all at the exams, you might not remember this. So but don't panic. This concentration is C, no, and we take this as C alpha reacted, C alpha produce, and this is C minus C alpha, but it's almost equal to C. Here we have C alpha and C alpha. Okay, right. So then you write Ka. We know Ka is equal to HCOO minus concentration into H3O plus concentration divided by HCOOH concentration. Ka is equal to, this is C alpha, this is also C alpha over C alpha squared over C squared alpha squared over C, that is C alpha squared, in case if you forget. Then alpha squared is Ka over C. means alpha is equal to square root of Ka over C. Sometimes in essay questions, they will even ask you to derive this equation. We have to do this. We have to do this and show. Right, and I'm not going to continue there from that point. So if you forget this equation, you'll have to do all these things and get to this point, and then you have to finish it off. Right, better. It's a small equation. If you put a little effort remembering this equation, Henderson's equation, and yeah, for H3O plus also we have a H3O plus is C alpha. Like that, if you can remember, it's easier for you. Moving on, 2011 done. Under buffer solution, don't know whether we missed some questions. There were questions under buffer solution. This is 2016 buffer solution question. Let me check if they have any. No 2007. So let's continue with pH. I'm focusing more on the most recent questions. Right. Next we have come up to 2011 question. Now it's the right. Let's focus on 77 first. Let's finish this off. 77 is the question from 2011. 77 is the question number in the Pesur book. Right, let's get started. Equal volumes of HNO3, pH equal to 2, and so when you say HNO3 pH equal to 2 means HNO3 is a strong acid, so directly I can say HNO3 H3O plus concentration is equal to HNO3 concentration because it's a strong acid, and that's going to be equal to 1 into 10 to the power minus 2 mole per decimeter cube. That is what I understand by this. HCl of pH equal to 1. Now HCl of pH equal to 1 means they are again H3O plus concentration resulted by HCl is equal to the concentration of HCl itself equal to 1 into 10 to the power minus 1 mole per decimeter cube. They were mixed, the pH of the mixture. I think we did this question at the class, but never mind, we'll quickly finish it off. This is that we discussed different types of mixtures, different types of cases for pH. First started with strong acid, 2 strong acids together, 1 weak acid and a strong acid, 2 weak acids together, 1 conjugate base, 2 conjugate bases together, weak acid mixed with a strong base. Likewise, we discussed around 7 to 8 cases. So this is one of those cases. And what's happening here? They are mixing HNO3 V volume with HCl V volume. So resulting solution will have 2V volume, 2V centimeter cube. Remember that. So here we have HNO3 and here we have HCl. The important part is the concentration, people. Concentration of HNO3 is 10 to the power minus 2, if not 0.01 m. Yeah, and this one is 0.1 m, 10 to the power minus 1. So first and foremost, we have to find the number of moles of HNO3, which is equal to Cv. Number of moles of HNO3 means, number of moles of H3O plus released by that as well, 0.01 V. A number of moles of HCl, it's equal to Cv again, and number of moles of H3O plus released by that, it's equal to 0.1 V. So from these two we can say, total number of moles of H3O plus ions released to the solution is 0.01 V plus 0.10 V, which is 0.11 V. So here finally we will have H3O plus ions released from both of them. Number of moles will be 0.11 V moles. So if you take the concentration of H3O plus, number of moles of volume, number of moles there 0.11 over volume is 2V this time, double. So the final answer is 0.055 mole per decimeter cube. Okay, people. Then I have to find the pH of that. H3O plus concentration now is equal to, for my convenience, I'll make it 5.5 into 10 to the power minus 2 mole per decimeter cube. If you want to find pH of anything, you need this. So, pH is equal to minus log H3O plus concentration, and minus log H2O plus concentration is 5.5 into 10 to the power minus 2. When you find pH of this one, 2 minus log of 5.5. I think should be 2 minus log of 5.5 should be roughly equal to 0.7. I think we can resettle to 1.3. This is how you do. We find the number of moles resulted by each, add them, find the total number of moles of H3O plus in the resulting mixture, and you need to divide it by 2V. Very important, because the volume became double when you mix both of them. And then you find the resulting H3O plus concentration, and using that you will find the pH, and which is 2. So in other words, the pH of the resulting solution will be between 1 and 2. That is something you should know, no? Both are acidic solutions. One is slightly less, the strength of this is slightly less, this is stronger. So when you mix, you will get a moderate one, but that doesn't mean you will get 1.5 exactly, because pH is pH doesn't work that way. pH depends on log. So you can't just add 1 and 2 and divide by 2 and put third answer. Completely wrong. You should know answer is either second or third. We might have to quickly find it this way. Okay, done. Then we'll move on to the next one. 76th one is a really cool question, people. 76th one, really good one. Okay, so let's quickly have a look at 76. In other words, 2011 once again, and this is again a qualitative question. Quantitative in the sense we are not going to put equations and all, but we need to understand what's going on here. So we are supposed to arrange these solutions A, B, C, D according to the order of their pH. There are two solutions given to us. There are two compounds. One is ammonium chloride, and the other one is sodium acetate. Now we came across sodium acetate in one of the previous questions a little while ago. Now ammonium chloride is a result of reaction between ammonia and HCl, and sodium acetate is a result of the reaction between acetic acid and sodium hydroxide. Now ammonia and HCl, ammonia is a weak base where HCl is a strong acid. HCl is a weak acid, sodium hydroxide is a strong base, which means ammonium chloride is a weak acid. This is a weak base. All right, so you should know when ammonium chloride, it will completely dissociate to ammonium ions and Cl minus ions. That will happen, and then that ammonium ion will react with water. Okay, wait. So this is a weak acid, this is a weak base. So pH, how about pH then? So pH, generally speaking, pH is usually higher for pH will be higher for who? This ammonium chloride should be lower than CH3 C double bond O Na. Why did I arrange them like this? Because ammonium chloride is a weak acid, and this one is a weak base. So first and foremost, we have to figure out this one. So people, I can definitely say pH, there are two solutions of ammonium chloride. One is A and the other one is B. A and B should be less than C and D. Between A, B, C, D we decide, but your answers must be like this. All right, so only one answer can be cancelled out, that is the fifth one, because in the fifth one they have put A and B first and C and D second. In all the other answers, A and B last and B, C and D first. So we have to do the work. Right, so first of all, let's focus on ammonium chloride. then this ammonium ion, what it does is it will react with water, and it will release who? H3O plus ions. It will release H3O plus ions, and of course NH3. So this is actually acidic. This is a weak acid, like we discussed. Weak acid, it releases H3O plus. So from this we can conclude something like this, people. What can we conclude? So when ammonium concentration is high, who is high, people? H3O plus concentration is going to be high, because if I have more ammonium ion, I will get more H3O plus ion. Let's say, for example, if I have 100 ammonium ion, and if those 100 ammonium ions are going to release 1 H3O plus ions, if I have 1000 ammonium ions, they are going to release 10 H3O plus ions. So more the concentration of NH4 plus, more H3O plus will be released, because this is C alpha, C and C alpha. The concentration, no. So if C increases, C alpha will also should increase, no. Common sense. When this increases, this also should increase. If H3O plus concentration is high, what will happen? pH when is low. Okay, we all, that's universal. We all know that when. Oh wait, I'll write it here, somewhere here. That's something we have to always remember, people. When H3O plus concentration increases, pH decreases, and when OH minus concentration increases, pH will increase. Okay, right. So when ammonium ion concentration is high, people, pH will be low. So pH between A and B, what can we say? What can we say? A has lower concentration of ammonium, B has high concentration of ammonium, so it should be this. A should have higher pH than B. I think since they are talking about ascending order, we'll write it in ascending order itself to avoid any confusions. I hope you guys understood this. If ammonium concentration is high, that means this will release more H3O plus. Concentration of H3O plus will be high. If concentration of H3O plus is high, pH is less. So B less than A, how many answers can be cancelled off? Answers with A last can be cancelled off. So we have to choose between 3 and 4. Then we'll go back to this one. Sodium acetate. Now sodium acetate, first and foremost, people, just like ammonium chloride, will completely dissociate to CHCOO minus and Na plus, and then that CH3OO minus, it's a base, it will react with water and it will be releasing OH minus and CH3COOH. So when you look at this, you should be able to understand that when you increase the concentration of this, you are actually increasing the concentration of OH ions released, OH minus ions released, because this is a weak base. Now it's a conjugate base. Good. Then what can I say? So when concentration of CH3 C double bond minus is high, concentration of OH minus is high. When concentration of OH minus is high, pH is also high. I have written it on top. Therefore, between C and D, who will have higher pH, people? Hurry up. Between C and D. Between C and D, who will be higher? This will be higher. D will be higher. It will be C. Because more concentration of base means, I think we don't have to waste our time that much. I just explained it a little too much. This is an acid, this is a base. If the concentration of acid is more, pH is less. If the concentration of base is more, pH is more. Without wasting all your time like this, but I just wanted to explain you how this, if you're wondering how this can act as a base, this is the explanation. How this can act as an acid, this is the explanation. All right. So when you combine these two people, obviously you will be getting the answer. D should be highest. That means the third is the answer. Okay, right. If you want a shortcut, you can first figure out weak acid and weak base, and then if acid concentration is high, pH should be less between them. If base concentration is high, pH should be high. Based on that also you can quickly decide the answer. Done. Okay, moving on. I think this one is no, this one is not relevant to pH. It's just a chemical calculation thing. And yeah. Does it have anything to do with? This has something to do with what methyl orange indicator. We haven't studied about indicators yet. So once we finish indicators, maybe we can come back to 2010. Good. Then we have this question 73 and 72 perhaps, and focus on them. 73 and 72. 73. What does it say? Consider the solubility product of FeOH2 in aqueous medium at constant temperature. If pH of the solution is increased from 8 to 9, the solubility of FeOH2. Okay, interesting. Now when you take FeOH2 solubility product and pH combined, see, solid, first it turns to Fe2 plus aqueous and 2OH minus aqueous. Alright, so if the solubility of this is x mole per decimeter cube, we know this is going to become x mole per decimeter cube, and here it is 2x mole per decimeter cube. That is how it works, no people? Okay. Now if pH of the solution is increased from 8 to 9, the solubility means x is the solubility of that. This x is solubility of FeOH2. So our OH minus concentration, it is 2x. Okay, OH minus concentration is 2x. Now now when pH, if you take pH when pH is 8, now this is what's happening now people. pH of the solution is increased from 8 to 9. So initially pH equal to 8 is turning into pH equal to 9. We have to compare the two situations. If pH is 8, pOH is 4, correct? No, not 4, 6. And if pH is 9, pOH is 5. Okay, why is that? Because we know the relationship between pH and pOH, because pH plus pOH at 25 degrees Celsius is 14 pKW. If pH is 6 people, what can I say? pH is 6, that means sorry, pOH is 6 means OH minus concentration is in fact how much? It is 10 to the power minus 6, right? And here OH minus concentration is 10 to the power minus 5, which can be written as which this is 1 into 10 to the power minus 6, and here pOH is 1 into 10 to the power minus 5, which can be written as 10 into 10 to the power minus 6m. So instead of OH minus concentration, I can put 2x, which is the twice of the solubility, 1 10 to the power minus 6. So look at x, it is when I divide this by half, so half into 10 to the power minus 6 m. This is the solubility of iron 2 hydroxide, and here again 2x is equal to 10 into 10 to the power minus 6, and that is equal to x is equal to 5 into 10 to the power minus 6. Now this is in fact half. We'll put half, 0.5 into 10 to the power minus 6. So what has happened to x people? It has increased by a factor of 10, is it? Did I make a mistake somewhere, people? Oh, does it decrease or increase? pH increases means OH minus concentration increases. Okay, I think I might have to consider it in a different approach, no, this time. Oh, yes. You don't have an answer like that, no? So what I could have done is I could have applied KSP for both the scenarios separately, no, people, because OH minus concentrations we know, yeah, and we have to find X. So they are altering OH minus concentration artificially. That's what they're doing. They have given all as the answer for this question. Because according to this one, we are getting the answer increases by 10 times. No? Increases, if we do it this way, we are getting an answer which says, so when you compare these two, I can say, so solubility increases by 10 times. But I have an issue. When OH minus concentrations changes like that, people, F2 plus concentration also should change. I did not take that into account. No, that is going to be a problem. I think they are adjusting OH minus concentration externally by adding a little bit of sodium hydroxide or something, because KSP will be constant for FeOH2. No? KSP will be constant because they are saying constant temperature. Where? Constant temperature here. So when they say constant temperature, that means we should say constant KSP. It doesn't change. So taking this as 2x is something a mistake. Now we can do this comparison only if FeOH2 is releasing this OH minus, if you get OH minus only from FeOH2, but at a given temperature, this x value will be a constant value. It can't change because KSP cannot change unless we add OH minus separately. So the way I approached, I don't think. What I should have done is this. Now if I write KSP for this, okay, KSP, listen to me carefully. OH minus concentration අපි මෙහෙම කරමු. So this is one way of approaching it. Yeah. So if pH is changed, people, listen to me carefully. What I'm trying to say, listen to me carefully. If pH is changed, KSP can't change. Now KSP is constant because temperature is constant. KSP can't change. So if you are changing the pH, that means you are changing OH minus externally, Fe2 plus concentration will also change. Fe2 plus concentration is equal to the solubility of FeOH2 because Fe2 plus ions are released only from FeOH2. OH minus ions are released from FeOH2 and someone else also is giving that OH minus concentration. That's how we can alter the OH minus concentration at constant temperature. So wait, this part, I'm a bit, this part, there's a problem. OH minus concentrations are okay. We have to substitute that and see what will happen to Fe2 plus concentration. Shall we try that now here? With these two values, 10 to the power minus 6 and 10 to the power minus 5 for OH minus. Let's see if we can find out, well, what is KSP. KSP, if I write the equation for KSP, people, that is equal to Fe2 plus concentration into OH minus concentration squared. Now one thing we can say for sure is this. What is it? When I compare these two, I can say solubility of FeOH2 equals to concentration of Fe2 plus ion. I hope you can understand that. Right. So first and foremost, let's apply this equation when pH is equal to what? pH is equal to 8. When pH is equal to 8, look at the equation KSP, that is equal to I'll take this as x1 into OH minus concentration squared. Where is OH minus concentration? 10 to the power minus 6 squared. x1 into 10 to the power minus 12. So x1 is equal to ksp divided by 10 to the power minus 12. Okay, and the other scenario where when pH is equal to 9, when pH is equal to 9, what is going to be ksp? Ksp doesn't change, constant. New solubility x2 into concentration of OH minus when pH is 9 is this, where 10 to the power minus 5, so it's 10 to the power minus 5 squared, that is equal to x2 into 10 to the power minus 10, and x2 is equal to ksp over 10 to the power minus 10 people. This is how we have to do. This is how we have to do. First equation, second equation. So when I divide the first one by second one by first one, I'll be getting x2 over x1 equals to ksp will get cancelled out, 10 to the power minus 10 over 10 to the power minus 12, which is 100. Increases by a factor of 100 is the correct answer. This is wrong. What I've done here is wrong, unfortunately. I'm sorry. This part is wrong. Because OH minus concentration is controlled from outside. So when you change OH minus concentration, Fe2 plus concentration will also adjust accordingly, because Ksp is constant, people. I think answer should be second. Anyone has this original scheme? Please check that, will you, for 2010. Or else don't know whether they are the people who made the paper also are confused about this and this. This is how you have to do it. I hope you guys understood this, because when you write this equilibrium, whatever the solubility of this, it will be always equal to Fe2 plus concentration, because Fe2 plus is released only by this. Hold on. 2010 29th MCQ. 2010 29th MCQ. Anyone has an original scheme? We need to check the original scheme, people, not these past paper books of Pesuru. It's better if we have an original scheme and we check. 2010. It's a good question, but it's a very good question, which allows us to, right, we'll double check, but I think this is how you have to do the question. Okay, this is how we have to do the question. We can't take this as 2x if it is if it is controlled externally. If it is controlled externally, it's better not to use that 2x. If they have given different pH, that means different OH minus concentration. Remember the condition, that is this is not POH, this should be OH minus concentration. Here I made a mistake, this should be OH minus concentration, sorry. See, we have different OH minus concentrations for different situations, and if OH minus concentration is different in different situations, Fe2 plus concentration will be different in both the situations, and Fe2 plus concentration is in fact equal to the solubility, because Fe2 plus is released only by FeOH2. So that's the argument I have. Okay, past paper book says all, Pesuru also says all, is it? I will check, but I think this is the method of doing that, people, and they are controlling pH externally by adding a little bit of acid to the solution. They are changing it. So I hope you can understand that, because the final solubility over initial solubility, when I divide them, I'm getting 100. So increased by a factor of 100 seems more reasonable than the previous method. Do like this. To substitute the concentration of OH minus and find the concentration of Fe2 plus in each. Concentration of Fe2 plus is the solubility, because this, if this is X, this is also going to be X directly. Okay, I think yeah, we've spent enough time for this question. We'll continue. I think answer should be second. Let's check the schemes, original schemes, and see, or else we'll have to go through some reviews and see why they have given it that way. Okay, right, then this will be the last question for this session, 2010. the pH of a monobasic weak acid solution is 3. The pH of the same solution upon dilution of 100 times is 100 times could be that we have done at the class. Can you say that in one without doing any calculations? It will be 4, no people, it will be 4. It will be 4. We have summarized that. Hope you can remember now. For a strong acid, if diluted by 10 to the power n times, we studied pH increases by what? pH increases by n. pH increases by n. For a weak acid, what do we study? For a weak acid, if diluted by 10 to the power n times, now 10 to the power n time means 10, 100, 1000, right? What happens to pH, people? pH increases by n over 2. So that's something we will have to remember. Otherwise everything you can't do questions. So what I'm trying to say is this. Example, let's say I have a solution of HCl. Which is at 0.1 m concentration. So here you see pH is equal to 1, people, pH is equal to 1, and then you dilute it by 100 times. Diluting by 100 times, then concentration of HCl becomes 0.001 m directly, because so pH becomes equal to 3. But on the other hand, if you have an acetic acid solution, let's say COOH, it is 0.1 m, pH of that could be 3. Let's say 3. It has a pH of 3, and then you dilute it by 100 times, and the acetic acid concentration of the acid will become 0.001 m, but pH will not become will not increase by 2, it will rather increase by 1. It will become 4. Because we are diluting by 100 times. When you say diluting by 100 times, it is diluting by 10 to the power 2 times. Please check your notes. We have done this properly in the notes. I have explained this. So for future references, it would be better if you can remember this when you want to handle MCQs. Otherwise you'll have to go through all this process. Or else, let's say you have forgotten this. Then what is going to be your plan, people? Now then we'll have to come up with an alternative plan, because sometimes you might forget it. Then the alternative plan is this. You have to compare the two solutions very quickly. They are talking about a weak acid, right? Weak acid is so there is a weak acid HA. It has pH of 3, and let's say the concentration of HA is C. Now they are diluting it by 100 times. Okay. Then HA will remain as it is. The new pH we do not know, but one thing we can definitely say is the concentration of HA solution, that is going to become what? C over 100, not 0.01 C. The HA concentration will reduce, but not H3O plus concentration. We have to find H3O plus concentration. So here, people, what is the H3O plus concentration for this scenario? If pH is 3, H3O plus concentration is going to be 10 to the power minus 3 m. Not only H3O plus concentration, A minus concentration is also going to be that, because we have only HA. So I think here we need to know the H3O plus concentration. If I go with Ka is equal to H3O plus concentration into A minus concentration over HA concentration. Now Ka is going to remain constant because it is constant at constant temperature, at same temperature. See, they have mentioned. So these two concentrations are going to be 10 to the power minus 3 into 10 to the power minus 3, and HA concentration is C. Alright, so it is 10 to the power minus 6 over C, Ka. Now for this, when you write Ka is equal to H3O plus concentration into A minus concentration divided by Ha concentration. Now instead of Ka, you can put this value 10 to the power minus 6 over C. These two concentrations are equal to each other, people, in a at equilibrium, so I can put it as H2 plus concentration squared over, for Ha you have put 0.01 C. So 0.01 C. Why did I put 0.01 C? Because the solution was diluted by 100 times. C and C will get cancelled out. So H3O plus concentration now becomes equal to H3O plus concentration squared becomes equal to 10 to the power minus 6 into 0.01, that is 10 to the power minus 8. So H3O plus concentration is equal to 10 to the power minus 4 mole per decimeter cube. Then what is pH, people? pH is equal to 4. In case if you have forgotten the summary, this is how you have to do it. Right, this is a weak acid solution. You can't just find pH, you have to go to Ka and then only you can find pH. So either way you can find it, but if you can remember this, it's just a snap of a finger. Within a snap of a finger you can get the answer and move on to the next question. If you are going to do like this, you are going to consume time which you could have invested on other questions. That's why I say these things are important. Right, good one. Right, so I think we have pretty much covered a lot of new things. If we can do all these questions, it would be great, but it's due to time constraints, we'll have to stop at this point. So you guys can now go through the other questions as well. We have covered up to 2010, which is nearly 12 years past papers.